Tell me when to go. I'm ready. All right, now I have a bunch of questions for you. Consider a horse pulling a buggy, a carriage. Is the following statement true? The weight of the horse and the normal force exerted by the ground on the horse constitute an action-reaction pair that are always equal and opposite according to Newton's third law. Now there's a couple ways of solving this or answering this question. You could just draw the force diagram, or you could just read it carefully and just remember that members of the force pair are always, if there's A on B, there has to be opposite B on A. So however you want to do it, but pause your video and figure it out. Okay, we're back. So let's just draw, let's see. Let's draw the force diagram. The weight of the horse. Now what's that? Okay, I'm going to draw it like this and you'll see why in a minute. So that's the weight on the horse, right? That's the mass of the horse times g. So that's Earth pulling down on the horse. But then the second one says the weight of the horse and the normal, I didn't have to do that, sorry. I didn't have to do that. All right. So weight, m horse g. Okay, then it says the normal force exerted by the ground on the horse. So there's a normal force. Now let's write it differently. Where did the thing go? So notice this is the force Earth on horse. This is the force ground on horse. So, are these members of the same force pair? No! Okay? Are they equal and opposite? Yes! But are they members of the same force pair? Not at all. Right? Because members of the same force pair, you can write it A on B, B on A. And remember, members of the same force pair don't act on the same object. Here the object is the horse. Here the object is the horse, right? We do the forces acting on the horse. So, no! Right? Right? The two members of an action-reaction pair act on two different objects. So the weight of the horse, the ground on the horse, both of these forces are acting on the horse. So what's the important thing here? Again, these forces are equal and opposite, right? But just because two forces are equal and opposite does not mean that they're members of the same force pair. That's the important thing. If they're members of the same force pair, you have to be able to write it like this. All right? I already know this one. That's okay. We already talked about it. A large truck and a small car traveling at any speed collide head-on. Regarding the forces, equal and opposite, right? Equal and opposite. Number 3. Okay, now regarding the accelerations in the previous question, which has the largest acceleration? Well, come on. You know that from experience, but you also know it from physics. A equals F over m. The mass of the car is much less than the mass of the truck. The forces are equal. If the mass of the car is less than the mass of the truck, the car has a huge acceleration. The truck has a small acceleration. All right, so the car's acceleration is much larger than the truck's. Okay. When you pull an object, okay, let's see, hold on. When you pull an object, like a table, across the floor, the forward force by you on the table is equal but opposite to the backward force by the table on you. It seems as though these two forces should balance out so that the table can't be moved. But the table does move. Okay, so I would recommend draw the force diagram, think. This is a tough one. This is a good one though. Draw your force diagram and think. And then, so pause your video. Come on. Okay, let's see. All right, so now you're back. All right, when you have a question like this, you always have to ask, what is the object? So, what's the object? Is it the table or is it you? It's the table, right? I don't care about you. Sorry. All right, the object is the table. That's what's moving, you know? So you draw the force diagram for the table. Now let's keep it simple. Let's just worry about the horizontal forces. What's the only force, horizontal force acting on the table? You. You on table. That's it. So why does the table move? Because there's only one horizontal force acting on it. I guess it's actually friction, right? But what we're saying is that this is larger than that, okay? But what they're talking about, they're saying, you know, look, they're saying there's a forward force by you on the table. So there's a force U on table, and then they're saying there's a force table on you. Now, are these two forces equal and opposite? Yeah! Do these two forces constitute a force pair? Yeah! But what does that got to do with anything? What does that have to do with the motion of the table? Okay? I mean, this is equal to minus table on you. All right, fine, whoopee. That's true. But if we're concerned with the force on the table, then the only important force is this one, right? Because this is the only one where the table is the object. I don't care about me. I'm not the object. It's the table that's the object. So again, you just draw the force diagram and bingo. So what's the answer? Right? Only one of these two forces actually acts on the table. And that's why the table moves, right? Okay. Oh, okay. Yeah, that's a nicer picture than this, huh? All right. So here's a force diagram. There's a normal force, there's a weight, there's a force U on table. These are the only forces acting on the table. So, well, there's friction, I guess. But let's say just frictionless, okay? So bingo, the table moves. That's all. All right. Oh, sorry. Now, why do we care about Newton's third law? Come on. Who really cares? Well, we're going to see, right? We're going to see. We're going to see that Newton's third law explains how we walk. All right? Now, which is kind of important, right? Or how a car accelerates or how a bicycle accelerates. Okay, let me rewrite Newton's second law. A equals the sum. I'm going to write it in a long way, which I will hardly ever do. Right? So the acceleration equals the sum of the external forces over the mass. Okay, can you help me for a minute? I forgot to tell you this. Have a chair. Okay, I'm not going to do this, but I'm going to pretend. All right, so. Okay, all right, so Sully is sitting on a chair with wheels, and his feet are off the ground. Now, if I were to grab Sully by his nose and pull, what would happen? He would accelerate. Agree? Okay, now Sully, okay, stay there. Okay, so you look at the chair, right? Rollers, yeah? Okay, so Sully's sitting in a chair, feet off the ground. Sully, I want you to grab your nose and accelerate yourself.
Okay. I can't do it.
How come? Thank you. Thank you. All right. Now, obviously, Sully is much stronger than me, right? No kidding. Now, I could accelerate Sully, but he couldn't accelerate himself. What's going on? Well, that's what this is all about. All right. In order to accelerate an object, all we care about are the external forces. The external forces. When Sully was sitting in that chair and trying to pull himself with his nose, that's an internal force. That doesn't work, right? And we saw it. Okay? So all we ever care about are the sum of the external forces. So, you can't get anywhere by pulling on your nose. Yeah? All right. Okay, let's talk about walking. Let's talk about walking. Now, I don't know what it's like outside, but it was nice before we started taping. So let's say we want to go to the beach, so we go to the beach. And we're at Hukilau Beach. And we're standing on sand, and the water's over there. So here I am standing, and I want to swim, you know? So that means that I have to accelerate to go, because I'm at rest. I have to accelerate if I want to go into the water. Now, according to Newton's second law, you know, F equals ma. So in order for me to accelerate, to start running into the water, there has to be an external force on me. External. So, what is it? So think about it. What is the external force acting on me that allows me to start running to go into the water? Well, and why did I choose? I mean, it's easy when you think about sand. If I want to run this direction, what do I have to do to the sand? I have to push it. I have to push it back, right? If I push it down, what good is that going to do? No good at all. If I push the sand back, what's going to happen? So let's look. So there's a force, me, on sand. And let's say that's that direction. Well, Newton's third law, right? Forces always come in pairs. So it has to be an equal and opposite force, sand on me. And what's going to be the direction of that? That way. So there you go. Okay? So that's what I mean. Newton's third law explains walking. How about if I'm not on sand? How about if I'm just on this carpet in here? Well, you know, when I'm walking, I'm pushing back on the carpet, right? I'm not pushing down on the carpet. That's kind of stupid, right? I'm pushing back on the carpet. And so it would be me on carpet, carpet on me. Equal and opposite. So, pause your video and draw the force diagram, please. Okay, we're back. Here it is. So there's the normal force, right? There's the weight, and there's the force that the sand exerts on you. So this force, we just give it a name. All right, just a name. It's called a propulsion force, okay? Propulsion force. Sand on you, propulsion force. Let's talk about a bicycle. What is the external force that causes a bicycle to accelerate? Well, here, think of this. Think of taking a piece of rope and tying the bicycle to the rope and tying the rope to the ceiling, and so the bicycle is like right here in midair. And then we put a person on the bicycle pedaling as fast as he or she wants. Is the bicycle going to accelerate? Certainly not. But on the other hand, if the bicycle hits the carpet and the person is pedaling, the cycle will accelerate. The bicycle will accelerate. So what is it? Well, the bicycle tire pushes back on the road, and so therefore the road pushes forward on the bicycle. So it's like this. So if the force, I'll say tire or whatever, tire on road, and then the opposite, the other member of the force pair is road on tire. So let's say that the bicycle is going that direction. So the force that the tire exerts on the road is that direction. So the road on tire is that direction. Okay, so everybody pause. Okay, just for fun, I want you to draw the force diagram, and I want you to include every force you can think of. So we're going to have air resistance, we're going to have everything. So draw the real, true life force diagram. So pause and do that. Okay, we're back. So here you go. You have the normal force, you have the weight, the force of the road on the wheel or tire, and then what do we have against us? We have air resistance, but also we have the rolling force, right? The rolling friction. Remember when we talked about friction, we had static, oh, we haven't talked about it yet. Oh gosh, forget about it, sorry. Anyway, we have something called rolling friction. Think about it. If your wheel is underinflated, it's going to be really challenging to ride the bike, right? So that's rolling friction. So rolling friction has to do with, the condition of the wheel or tire, if it's full or not. It also has to do with the condition of the road, if it's smooth or if it has all sorts of rocks and everything on it. We'll talk about it, don't worry. Here, let's talk about a rocket. Think about a rocket. So we have a rocket, and let's just say it's in deep outer space. So we're far away from everything, right? Hardly any air. It's almost like a perfect vacuum, So here's this rocket in deep outer space, and rockets can still accelerate. They can speed up, they can slow down, they can turn. How can they do that in a vacuum, in a perfect vacuum? Well, I think I have a picture of it. Yeah, here we go. All right. So this is a rocket engine. This is from NASA, the United States Space Agency, right? So what does a rocket engine do? It pushes out air, right? There's air in the rocket engine cylinder, okay? So that's where the air is, just in a rocket engine cylinder. So the rocket engine pushes out air, pushes the air this way. So what does the air do to the rocket? It pushes it that way, right? So it's just Newton's third law, Okay? So the exhaust flow pushes backwards, and then the engine pushes forward. So a rocket can actually accelerate in a perfect vacuum. So here, let's do this again. So you have force, rocket on air, or rocket engine on air, whatever. Then you have the force, air on rocket. And again, they're equal and opposite. Equal and opposite. Okay. Is this theoretically possible? So what are these guys doing? They're throwing out shoes. Okay, would it work? If this rocket were in deep outer space and these guys had a whole bunch of shoes and they're throwing out their shoes, would it work? Yes, it would work. It's exactly the same thing as a rocket engine, right? A rocket engine shoots out compressed air, or air. Well, this is just shooting out shoes. Same principle. Same principle. Rocket on shoes, shoes on rocket. This would work. Now, obviously, it's not going to work very well, but I mean, the physics principle is perfectly correct. All right, I have two questions for you, and each of these two questions has more than one correct answer. Okay, you are standing still on the floor. Which of the following statements must be true? So pause your video and figure it out. All right, we're back. Let's see. You're standing still on the floor, so your acceleration is 0. That's correct. Number 2, there are no forces acting on you. That's total garbage, right? There's the normal force and there's the gravitational force. So 2 is wrong. 3, the net force acting on you is 0. That's correct, right? Net force means the total force, or the sum of the forces. Okay, 4. By the way, I'm trying to trick you on this one and the next one, so be careful. 4, the normal and gravitational forces exerted on you cancel. They are equal and opposite. Totally correct. All right, so the ones that are correct, 1 is always true, 3 is always true, 4 is always true. Okay. Now let's do this one. Okay, so read it, pause your video. All right, you're back. Okay, you're sitting still on the floor. Which of the following statements is always false? All right, your acceleration is 0. That's true. 2, there are no forces acting on you. That's false. 3, the net force acting on you is 0. That is true. 4, the normal and gravitational forces exerted on you cancel. They're equal and opposite. True. 5, the normal and gravitational forces exerted on you are members of the same force pair. False! Why is this false? Because both of these forces are acting on you. and members of the same force pair don't act on the same object. Okay? Simple as that. All right, let's do a real challenging force diagram. So pause your video and read it and draw the force diagram. All right, you're back. We're back. This is a tough one. Okay, so all we're going to do is draw the force diagrams, right? We don't want to solve it. So basically, okay, so this mass is on this mass, all right? And we're pushing on it. And let's see. This thing does not slide down. Now look at it. This is frictionless. This is frictionless. But we're going to push it at one particular force, so this thing does not slide down. Ooh. All right, but anyway, all we want to do is draw the force diagrams, okay? That's all we want to do. So let's start with M1. All right. So what are the forces acting on M1? Okay, so let's say that this, all right, so this is the slant, you know. So that is this surface right here. Okay, so what are the forces acting on M1? Well, you know, this is a big deal. I didn't really need this, I guess, right? Whatever. Okay, so here's the object, all right? Yeah, whatever. This is the axis, right? So here's X and Y. Okay, so what do we have? We have weight. We always have weight. So this is weight. I'll say weight 1, which equals m1g. Now, no friction. What else is there? Well, these are touching, so there's the normal force. And the normal force is perpendicular. So there you go. So there's the normal force. Okay? Yeah, okay. That's it. All right? So there, however, that's it. Just the normal force and the weight. Okay? Let's do the second one. Okay, now what are the forces acting on M2? Well, there's F, right? So there's F, there's the weight. Say the weight 2 equals m2g. Now wait a second, force pairs, right? What's this normal? Isn't this really the force that m2 exerts on m1? Isn't that what it really is? Yeah, that's what it is, right? So if there's a force m2 pushing up on m1, isn't there equal and opposite? Yeah. So it has to be like that. So this is a force m1 acting on m2. So sometimes, you know, sometimes it's useful to write it like this. It's kind of long, you know, but it's useful. And then we have here, we have N2, right? And what's N2? N2 is the force of the, what do you call it? So this is the floor, okay? So it's the floor on M2. And I don't care about the force M2 on floor, because I don't care about the floor. So that's it. All right, that's it. So study that, make sure you understand it, because I think that's kind of a tough one. All right, let's review a little bit. Oh, there's my beautiful pictures. All right. Okay, great. Okay, so now we know what does and doesn't constitute a force. Have to have two objects, two or more objects. We talked about gravity and normal and I guess tension. We're able to identify specific forces acting on an object. This is the important one, right? Draw the correct force diagram. The process of understanding the connection between force and motion, F equals ma. And then this is Newton's third law. Okay, so let's just quickly review. A force is an interaction between two or more objects. So for this, so here, Earth is pulling down on me, but I am actually pulling up on Earth, right? Two objects, me and Earth. Newton's second law, F equals ma, the perpendicular force or the normal force. Make sure you can draw the force diagrams, okay? Just make sure you can draw a force diagram. Newton's third law, force pairs, A on B, B on A with a minus sign. Propulsion forces like walking and bicycles and cars and things like that. And that's it. So we'll see you later.